This lesson has the title Implicit Differentiation. Implicit means implied. Explicit means expressed. Explicit is direct. Implicit is indirect. Most of the equations in foundation courses in mathematics are explicit. In this lesson, we shall address and emphasize equations which are implicit. Let's see if we can make the distinction. Look at Roman numeral 1, this function. You see y equals. That is easy to graph. Put it into your calculator and graph it. Why is it easy to graph? Because we have it written as y equals expression in terms of x. It's also easy to take the derivative of this, find y prime, okay? That's an example of an explicit. In other words, it's explicit what y is. So look at Roman numeral 3. This is not an explicit because it's not written y equals. So it's going to be difficult to graph it, and it's going to be difficult to take its derivative. However, we can make this function explicit by moving the x squared over by subtracting it from both sides and taking the square root of each side, and we get this. And we can graph this. We solve for y. Y squared is 25 minus x squared, so y is the square root of 25 minus x squared. However, when we graph this, we're going to only get a semicircle, the top part of the graph. But remember, when you take the square root, it's plus or minus. So we take the negative of this quantity, graph that, and we get the entire circle. So this is an implicit function, but can be made into explicit. And for taking the derivative, we would do the same thing, and we would write this to the 1/2 power and take the derivative using the chain rule, and that would be the derivative. So we have a function that's not explicit, but we can make it implicit. Let's look at Roman numeral 5. Now here, to solve for y in order to graph, it's not going to be easy. We say perhaps impossible. We cover ourselves here by saying perhaps, because there are ways probably to graph this, but not something that we're going to discuss now. One is you could just create a plot box, assign values to x, find out the y, or you might use something, another graphing system, rather than the rectangular coordinate system, which we use something called polar coordinates, which are circular graphs, but that's beyond the scope of this course and this discussion. So we're just going to say perhaps impossible, which also brings us to look at it again. Finding y prime is not going to be easy. We say difficult, perhaps impossible, or is it? And that's what this lesson is all about. Is it impossible to find y prime? And remember, the thrust of calculus is finding the derivative, not really graphing. Graphing gives us a picture, and derivative is slope, and so the graph gives us information that's helpful. But remember, we really are interested in finding derivatives, certainly in the first part of a calculus course. So let's investigate how we would find the derivative here. So what we've done here is we have rewritten our function from the previous slide. And where are we going to start? Well, remember, y is f of x. Y is f of x in mathematics. So why don't we, everywhere there is a y, let's substitute in on f of x. So this becomes x squared 2 times f of x, quantity f of x squared plus x cubed. And now let's take the derivative. Let's take the derivative. Well, the derivative of x squared is 2x. Now, the derivative of f of x is f prime of x. Now, f of x is not just x, it's an expression in terms of x. So we take the derivative 2 times. So we call that f prime of x. Now, in this case, we have an expression to a power. So to take the derivative, we're going to have to, it's 2 times f of x to the first power rule there, but we've got to take the derivative of the expression. In other words, we've got to use the chain rule. And of course, the derivative of x cubed is 3x squared. Let's run through this one more time. Derivative of x squared is 2x. The derivative of this is 2 times the derivative of f of x, which is f prime of x. The derivative of this is 2 times thing to the first power. Remember, we subtract 1, exponent 2. But then we've got to take the derivative of the quantity. That's the chain rule. And then, of course, we can take the derivative of x cubed is 3x squared. Now, pause for a minute. We would not be able to do this if it were not for the chain rule. So we are assuming that you have already studied a lesson on the chain rule, or this step right here probably doesn't make a lot of sense to you. Okay. So now, what is that? Our goal here is to find the derivative. So let's just rewrite this thing and let's find the derivative. Well, what is the derivative? F prime of x. In other words, we want f prime of x. So let's see if we can find f prime of x. Well, we have an f prime of x here, and we have an f prime of x over the right-hand side. Let's take this quantity right here and bring it over to the left-hand side of the equation. In other words, we'll subtract it from each side. And this 2x doesn't have an f prime with it, so let's move it to the right-hand side of the equation. Now, do you see what we've done? We bring this over, and we put a subtraction, and we bring this over, we put a subtraction. Now, keep in mind what our goal is, to find f prime of x. Well, we have an f prime of x here and an f prime of x here. So can we factor out an f prime of x? And yes, we can. And when we do, we have a 2. And we have a minus 2 f of x equals this. So f prime of x is equal to this divided by this. Now, our goal is to find, we originally had a function in terms of y and x, but can we not, since y is f of x, can't we put y back in for f of x? And so we do. So f prime of x, or y prime, is this. And what we have done is we have found the derivative of a function without isolating the y. And that is what our goal was. So we've solved that problem. Now, it seems a little involved. So let's see if we can create a menu. Here's what we're going to do. Step 1, we're going to take the derivative of everything as usual. But if it's a term that has a y in it, we're going to put a y prime with it. So let's see what happens. The derivative of x squared is 2x. The derivative of 2y is just 2. That's a y term. Put a y prime with it. The derivative of y squared is 2y. That's a y term. Put a y prime with it. The derivative of x cubed is 3x squared. That's step 1. Now we're going to get our y primes on one side and our non-y primes on the other side. Now, it really doesn't matter which side you move to which, okay? And we'll talk about that. And it doesn't matter. We'll show you before we finish. Leave this page. We're going to move this quantity over to the left side, okay? And the non-y prime terms over to this side. That's what we've done. So that's step 2. What did we do? We took the derivative as usual, but every time it's a y term, we put a y prime with it. What did we do in step 2? Get y primes on one side and non-y primes on the other. What are we going to do next? Factor out a y prime, and now solve for y prime by dividing each side by this, and there's our answer. Now, let's address what if you had, instead of moving this to the left, you had pulled this to the right. And instead of moving this to the right, you had moved this to the left. It would not matter. The only difference is this is the answer you would have gotten if you had moved the y primes to the right and the non-y primes to the left. Now, how do these two answers compare? Well, let's take this answer and multiply the numerator by -1. And what do you get? 2x minus 3x squared. And let's multiply the denominator by -1. And what do you get? 2y minus 2. So they are equivalent. If you multiply the numerator and denominator of the numerator and denominator by -1, or negate each other, whichever way you want to look at that. Of course, -1 over -1 is 1, and multiplying by 1 doesn't change anything. So now we have a menu, and we can follow that menu, and as we get better, we probably can leave out some steps. Now, you'll never be able to leave out step 1, because that's what makes it work. And you'll never be able to leave out step 4, because that's the answer. But as you get better, you may be able to wean yourself off of doing step 2 and step 3 and do some of that in your head. And we are aware of that. You need to be aware of that as well. But here in the beginning, we're going to go through all 4 steps. Now, before we leave this, there is an alternate notation many textbooks use, and your instructor may be using it as well. And that the only difference is, instead of using the y, anytime you take the derivative of y term, you put a y prime with it. Anytime you take the derivative of y term, you put a dy dx with it, and then everything else is the same. Dy dx on one side, non-dy dx terms on the other. Factor the dy dx, solve for dy dx. Now, we choose to use this y prime notation for several reasons. One is it takes up less space. If you're just using a standard typing, not into a word processor for mathematics, it's easy to make the notation y prime than it is to dy dx. That said, it really doesn't matter. It really doesn't matter which one you use. And so we're going to pretty much be using the y prime notation in this lesson. And there's a place we're going to come to, or part, I guess, rather than place, we will come to near the end of this lesson where the y prime notation has it all over the dy dx notation in our way of thinking. So each method has a situation where one is better than the other. As I said, we're going to use the y prime notation, but you ought to know both of them. There's a topic called related rates where we're going to use the dy dx notation, okay? And there's sections in calculus topics called the differential where you want to use the dy dx notation. So they both have their strengths my estimation. So we'll leave this, and now we'll go look at some examples. So let's look at example 1. Y to the fourth minus x squared is x cubed plus 3y. Find y prime. So let's go through our menu. Derivative of y to the fourth is 4y cubed. That's a y term. Put a y prime with it. Derivative of x squared is 2x. Derivative of x cubed is 3x squared. Okay. Derivative of 3y is 3. Put a y prime with it. We're going to bring this over to the left, and we're going to bring this over to the right. We're going to factor out a y prime from this term, and we're going to solve for y prime, and we're done. Let's look at example 2. Find y prime. Derivative of 5x squared is 10x. Derivative of y squared is 2y. Put a y prime with it. Now here we need the derivative, so we're going to have to use our product rule, which is first times the derivative of the second. Well, the derivative of y to the fourth is 4y cubed. Put a y prime with it. Plus the second, y to the fourth, times the derivative of x cubed, which is 3x squared. Let's leave this term here and bring this term over. And when we do, we are going to pull the 4 out front, like we like to have numbers out front. Okay. And then we're going to bring the 10x over here so it can be with this term. And we're going to pull this 3 out front because we like the 3 out front. We're going to factor out a y prime. And then we're going to solve for y prime by dividing each side by this quantity. There's your answer. Now this problem is a little more difficult because we have to use a product. Okay, so we're stepping up our level of difficulty. Let's look at example 3. Let's find y prime. Well, the derivative of e to the 3x is e to the 3x times the derivative of 3x, remember the chain rule, is 3. The derivative of y squared is 2y. Put a y prime with it. The derivative of e to the 2y is e to the 2y times the derivative of 2y, which is 2. Put a y prime with it. And the derivative of x cubed is 3x squared. Y prime's on one side. We're leaving this one alone, and we'll bring this one over. And then we'll leave this be and bring this over. We'll factor out a y prime from this. Now we'll solve for y prime. Keep in mind, if you worked it by bringing the y prime to the right, this answer would be 3 e to the 3x minus 3x squared over 2 e to the 2y minus 2y. Now, what's the thing in this one that makes it different? This one involves the chain rule. Previous one required the product rule. So this one is harder in its own way than the second one. They're both harder than more difficult than the first one. So you want to make sure you understand the first one before you really leave example 2 and 3. Let's bring in some trigonometry. Find y prime. The derivative of the cosine is negative sine. The derivative of the secant is secant. Tangent, that's a y term. Put a y prime with it. Derivative of the cosine, sine, excuse me, is the cosine. The derivative of the tangent is the secant squared. And that's a y term. Put a y prime with it. y primes on one side, and it seems like we're always bringing it to the left, and non-y primes to the right. Factor to y prime, solve for y prime, this divided by this, and leave it. See the pattern. So this, once you accept the fact that there's a pattern, this is not really too difficult, provided you know the chain rule, provided you know the product rule, and provided you know the derivative of e to a power and know the derivative of your various trigonometric functions. So we're okay, provided you know those. Now we're really upping the ante a little bit. We've got everything in the world going on here. Okay. Derivative of the sine is the cosine. So the derivative of sine of xy is the cosine of xy. The derivative of xy, that's a product. So we've got to use a product rule. In other words, chain rule says you've got to take the derivative of the expression. So it's going to be first x times derivative of y, which is 1, put a y prime with it, plus the second, which is y, times the derivative of x, which is 1. And likewise, the derivative e to the xy is e to the xy, and we've got to take the derivative of this, and this is also x times y, so we get this same thing. First times derivative of y is 1, put a y prime with it, y times derivative of x, which is 1. Now we have an intermediate step here that we didn't have in the others. Before we can start moving the y primes to one side and the non-y primes to the other, we're going to have to multiply this out. So we're going to multiply this times this, and this times this, okay? And this times this, and this quantity times this. Okay, we're using the distributive property from algebra. Okay. Now we're going to get our y primes on one side, so we'll leave this one alone and we'll bring this one over. And we'll leave this guy alone and bring this individual over. We'll factor out a y prime since we have one in each of these, leaving us with this. And now we'll divide through by this, and we have our answer. And we've only done 5 examples, and they're getting harder. They're getting harder. You have to be very organized in your thinking when you do calculus. And that's probably one of the biggest indicators of things that people might find interesting about people that can do calculus, is that they have to be extremely organized in their thinking. And for some people, areas of work, that seems to be a necessary characteristic. So make sure you can do the first problem. We go back to that, because if you can't do the first problem, then you don't understand implicit, because that's about as simple as we can make the problem. Okay. One last topic, finding y double prime. Now, this may be beyond what you're doing in your course, okay, but we want to cover that in this course, just in case you need to find the second derivative implicit. So let's take a problem here. X squared plus 3y squared equals y cubed plus x cubed, find y double prime. Now we're not getting fancy with this one. There's no chain rule. We don't want to have a chain rule problem here or a product rule problem, because finding the second derivative is a task within itself. So we want to keep this simple. So finding the first derivative, if you're going to find the second derivative, you've got to find the first derivative. So we're going to find the first derivative. So the derivative of x squared is 2x. The derivative of this is 6y, put a y prime with it. Derivative of this is 3y squared, put a y prime with it. The derivative of this is 3x squared. Y primes to one side, we're moving to the left. Non-y primes to the right. Factor to y prime, solve for y prime. So we have the first derivative, and that's not difficult. We also have put 5 red stars, asterisks, whatever, next to it. That means that is very important to the ongoing of the problem. And if that is not correct, then the second derivative is not going to be correct. But we've talked about that already in this series of lectures. When we did the second derivative, we said one of the downsides of finding the second derivative is if your first derivative is not correct, your second derivative is pretty much doomed, is it not? So we're going to take this and we're going to go to the next slide. And what we're going to do is we're going to take the derivative of this thing. That's going to be y double prime. We're going to have to use the quotient rule. So let's see. It's denominator times derivative of the numerator minus the numerator times the derivative of the denominator. When we take the derivative of the denominator, if you look back, some y, so we're going to get some y primes. Okay. Denominator times derivative of the numerator minus numerator times derivative of the denominator all over the denominator squared. So what we're going to do here is simply pretty much recopy this line right here, except that we're going to factor out these 2 y primes. Okay, that's all we've done is in this term right here, we factored out a y prime, which means this will be a 6, and this will be a negative 6y and a y prime. That's all we've done here. But it looks messy, doesn't it? Yes. What we're going to do next is we're going to, in the place of y prime, we're going to put this quantity. Now, where is this quantity coming from? That's this thing right here with the red stars by it. In fact, to emphasize that, this is red. We have it. Now, that really looks like a mess. This thing is a fraction, and the numerator has a fraction in it. We call that a complex fraction. Well, there's something you may or may not have been taught. When you have a complex fraction, one of the things you can do is multiply the numerator and denominator by the least common denominator. Okay? Which in this case, we're going to multiply the numerator and denominator by 6y minus 3y squared, numerator and denominator. When we multiply this quantity by 6y minus 3y squared, that gives us 6y minus 3y squared times itself, so that's this. Okay. When we multiply this part by 6y minus 3y squared, guess what? This vanishes, does it not? 6y minus 3y squared times this, we can cancel this out. And we're left with this and this, and we got 2 of those, so that's squared times this. And of course, when we multiply the denominator by 6y minus 3y squared, we get 6y minus 3y squared cubed. And for all intents and purposes, we're through the problem. If you wanted to say find the y double prime for a given xy at a certain point, and you just want a numerical answer, this is fine. We're not going further to try to simplify this into neither. Generally speaking, if all you want is to find an answer, numerical answer given an x and y, this will do the trick. Now, we will say to you that people using the dy dx notation, it's going to seem a little more cumbersome doing this problem with the dy dx notation than it is with the y prime notation. That's only our feeling, maybe not your teacher's feeling, but at any rate, we're glad here that we're using the y prime notation. And so that's finding the second derivative. And I would only look at this if you find out that it's something you need to know. Otherwise, it's not impossible. You've just got to be extremely careful. But notice how nice it fell into place. What looked like an entire disaster, especially here, became rather nice. Those things canceled. Let's conclude this lecture by taking care of something that we said earlier when we did the power rule. Remember when we did the power rule, y equals x to the n, and y prime turned out to be n times x to the n minus 1. We specified that n was a non-negative integer, but we worked problems where the n could be negative or fractional or whatever. Okay, and we said we would address that later. Now, if you've been looking at this series of lectures and you've done the quotient rule, you see that we have taken care of the fact that when n is negative, took care of that, find that in that lesson. But what if now n is irrational? I'm sorry, rational, not irrational. That'll come later. Rational, that is a fraction. What would you do for that? And we need implicit to do that. And that's why it's saved for here. So let's consider y equals x to the n, where n is a fraction. That is an integer over an integer, a rational number, p over q, where p and q are positive integers. So that means we can write y equals x to the n as y equals x to the p over q. Okay. Now what we're going to do next is we're going to raise each side of the equation to the q power. Now when you raise y to the q power, it gives you y to the q. And when you raise x to the p over q power to the q power, remember when you raise something to a power raised to a power, you multiply exponents. And when you multiply p over q times q, you get just p. Now let's take the derivative. The derivative of y to the q. Remember now q is a positive integer. This is why it says positive integer, because we know the rule is true. We derive that for non-negative integers. Okay? So we can use the power rule here, which is q times y to the subtract 1 from q minus 1. That's a y term, put a y prime with it. Likewise, the derivative of x to the p is p times x to the subtract 1 from the exponent, and that gives us that. Okay. Now let's solve for y prime. So we do by dividing each side of the equation by this, and this gives us this. Okay. Now we come over here, and what we've done here, the difference between this term and this term is that we have substituted in for y, it's equal x to the p over q power. Okay. We'll make that a little larger for us to see that. And now what I'm going to do is the only thing I'm doing here is I'm going to multiply this, this times this. Now, when you multiply p over q times q, you get p, and p over q times -1 is negative p over q. Okay. Now, notice I have x to the p minus 1 and x to the p minus x to the p minus p over q. And so when you divide, you subtract exponents. So I'm going to take this minus this exponent. And when you do, you get p minus p, that disappears, and you get minus 1 minus a minus p over q, which is minus 1 plus p over q, or p over q minus 1. And we're done. We have proven it. You say, what did we prove? Look, we want to show that the power rule works for p over q. If it does, that means you've got p over q in front, which we do, and you subtract 1 from p over q, which is what this is. So we have proved that it's true for a rational number. So we don't have to make apologies for the fact that we apply the power rule for fractions. So we've covered that. If you're not satisfied, that makes no sense. Let's take a problem and let's do that. This is what we just did for a special problem, x to the 2/5 power, and do exactly what we did there. Let's raise y is x to the 2/5. Let's raise each side to the 5th power. That's y to the 5th. Multiply exponents when you do that, so that gives you x squared. Then we do the implicit 5y to the 4th, put a y prime with it, 2x. Solve for y prime, gives you this. Now put back in the place of y, it's equal x to the 2/5 to the 4th power. That's going to be, you multiply exponents, that's going to be x to the 8/5. And when you take and subtract exponents, remember this would be x to the 1st power, which is 5/5. 5/5 subtract 8/5 is -3/5. And so that works for a special problem when the fraction is 2/5. But with the proof, we showed it works for any situation for where the numerator and denominator are positive integers. And so we've probably shown everything we can on this. Hopefully you realize that that the order that the calculus courses are set up is in such a way that you cannot do certain topics until you cover and develop certain skills or add to your toolbox. So we've got another thing in our toolbox, and that's called finding the derivative implicit. So this concludes this lesson.